Problem 4.4. Determine whether the following series are absolutely convergent, and if not, whether they converge conditionally. Okay, so we have 8 series, and all of them are of alternating terms. Okay, so as you can see, those almost all of them have this term -1 to the n. Okay, so that implies that every term will have a different sign, right? So this is the n -1 to the n, all of this. And the only one that doesn't have this pattern is the second series, the sign of this thing. But we will see how to work with this so that it has the same form as this. Okay, this is also an alternating series. Okay, so alternating series, they either converge absolutely, which means that the sum, wait a minute, the sum, yeah, from n equals 1 or to infinity of the absolute value of a sub n is smaller than infinity. So this is absolutely convergent, right? So that means the series of the terms taking all positive terms, so the associated series of non-negative terms, then this is absolutely convergent. Well, but if this is not, if this is divergent, but the series of alternating terms is convergent, then we say it is conditionally convergent. Okay, and the way to check if this series is convergent is using Leibniz test. Okay, which says that if we have a series like this, he says if we have a series like this of alternating terms, okay, and a sub n is decreasing and goes on to 0, then this series is convergent. Okay, so that's test Leibniz test. Okay, so we're gonna use this these two definitions and Leibniz test to solve this problem. Okay, so let's start with the first series. Okay, the series from n equals 2 to infinity of -1 to the n, the logarithm of n. Okay, as usual, the series with the logarithm start at 2 because the logarithm of 1 is 0, so it doesn't make any sense to have 1 over 0. Okay, so the series of absolute, so okay, a sub n is -1 to the n, 1 over the logarithm of n, right? So the series of from 2 of the absolute value of this, the absolute value of -1 to the n is going to be 1, so then we have 1 over the absolute value of the logarithm, but the logarithm for natural numbers greater than 1 is positive. Okay, so then we have this, right? Now we know that this series is divergent, okay, because of the comparison test. We know that n is greater than the logarithm of n, so that means, well, for n greater than 2 or equal than 2, right? Sorry, let me write it correctly. For n greater or equal than 2, which is the interval that we're interested in, n is greater than the logarithm of n, which means that the logarithm of n, 1 over the logarithm of n is greater than 1 over n. Okay, but the series of 1 over n is divergent, so this implies that the series associated with 1 over the logarithm of n is divergent as well. Okay, using the comparison test. Okay, so this series is not absolutely convergent. Okay, now is it conditionally convergent? Is this series convergent? Well, we can apply now Leibniz test. Okay, so he says we have this kind of series. Okay, now here a sub n here is 1 over the logarithm of n using his terminology, right? And well, he says if this goes to 0 and it's monotonically decreasing, which is the case, right? Because the logarithm of n is a monotonically increasing function that goes on to infinity. So 1 over the logarithm of n is monotonically decreasing and its limit is 0. Okay, so Leibniz test ensures that this series is convergent. So the result is that this is conditionally convergent. Okay. Okay. So this is the strategy that we will follow for the rest of the series. Okay. Now let's go for the sign. Okay. This doesn't look at first sight as if it's an alternating series, right? We have the sine of pi n plus 1 over n, right? From n equals to 1 to infinity. Okay, so let me draw the sign, okay? If I can do it correctly. So we have this, and this, okay? A periodic function, we know. And so this is x, and as you can see, this we're only taking the values that are close to it. So this is pi, right? This is 2 pi. This is 3 pi. This is 4 pi, and so on. Okay, right? The 6 pi, 7 pi, right? So now what it says is the sine of pi n, so when n equals 1, the sine of pi plus 1, okay? So pi plus 1, let's see, it's something like this, okay? This is the first value, sine of pi plus 1. Now, when n equals 2, this is the sine of 2 pi plus 1 half. So let's see, maybe it's this thing here, right? This is the sine of 2 pi plus 1 half. Now, when n equals 3, this is the sine of 3 pi plus 1/3, so maybe it's something like this, okay? Sine of 3 pi plus 1/3, and so on with 4, 5, 6, 7. Okay, so as you can see, if you only look at this point that I'm drawing, each alternating, so each point has the different sign from the previous one, right? This is an alternating series, right? Okay, and it's also getting closer and closer to 0, but we will see that later on. Okay, so this is kind of like the graphical way to see it. There's also an algebraic way to see it, because we know that the sine of x plus y is equal to the sine of x times the cosine of y plus the sine of y cosine of x, right? This is the formula for the sine of the sum. Now here x is pi times n, right? And y is 1 over n. Okay, so this is equal to the sine of pi times n times the cosine of 1 over n plus the sine of 1 over n times the cosine of pi times n, right? And this is equal to the sine of pi times n is 0, right? All the zeros of the sine have this formula, so this form, sorry. Okay, so this term goes to 0. And then we have the sine of 1 over n, and then the cosine of pi times n is when n is 1, the cosine of pi is minus 1, and then when n is 2, when the cosine of 2 pi is 1. So then if you look at the function cosine of pi n, this will be taking the values minus 1, 1, minus 1, 1, minus 1, and so on and so forth. Okay, so this expression, the sine of pi n plus 1n, is equal to minus 1 to the n times the sine of 1 over n. Okay, so we can rewrite this like this. Okay, so this is exactly the same thing that we have said here with this graphical demonstration, right? So this is minus 1 to the n sine of 1 over n, right? So this is also an alternating series. Okay, so let me erase all this. And now we can do the thing that we did for the logarithm before, right? So we have, first of all, we check if this is an absolutely convergent series. So we have the series of the sine of 1 over n, but the sine of 1 over n, when 1 over n is very small, is asymptotically equivalent to 1 over n, okay? So this series is divergent because the harmonic series is divergent, okay? So this is not absolutely convergent. Now we have the original series, the sine of 1 over n, and again, so this series is, sorry, this term here is asymptotically equivalent to 1 over n, and so we know that the limit of this is going to be 0, and it's also monotonically decreasing, so this is convergent. Okay, the original alternating series is convergent, so it's conditionally convergent, okay, because it's not absolutely convergent. Okay, okay, next one. 3. Let's see. The sum from n equals 1 to infinity of minus 1 to the n, the arc tangent of 1 over n squared, right? Well, what is this absolutely convergent? We have the arc tangent of 1 over n squared, right? Now we know that the arc tangent of 1 over n is asymptotically equivalent to 1 over n, right? So the square of this is asymptotically equivalent to this, okay, which is 1 over n squared. But the series of 1 over n squared from n equals 1 to infinity is convergent, okay? So this means that this original series is convergent. But this is the absolute, the series of the absolute terms, so this series is absolutely convergent, okay? And this implies that the series is also conditionally convergent, okay? So if you're absolutely convergent, you're also well, sorry, not conditionally convergent, because that means, but that means that the original series with the alternating terms also converges, okay? Okay. Now 4. This is the sum from n equals 1 to infinity of minus 1 to the n of the arctangent of n squared. Now, if you remember the arctangent, okay, so this is n, well, yeah, let's call it x or something, it doesn't matter, okay. The arctangent is this function that at minus infinity is close to minus pi halves. It crosses 0 here, and then it goes on to pi halves when n goes to infinity, okay? So this term doesn't, so if we compute the convergence of this series, this is not going to be convergent because the term, the general term of this series doesn't, the limit of this term is not 0, right? And so this is a sufficient condition to say that a series is convergent, sorry, divergent, okay? So in order for a series to be convergent, a necessary but not sufficient condition is that this limit is 0, okay? But if its limit is not 0, we can say that the series will not be convergent, okay? And it also is not conditionally convergent because, again, if we apply Leibniz test, this a sub n here, which is again the arctangent of n squared, is not monotonically decreasing, and its limit is not 0. Okay, so this series is not convergent, or you could say it's divergent. Okay. Now 5. 5 is the sum from n equals 1 to infinity of minus 1 to the n, square root of n squared minus 1 minus n. Okay? So as usual, okay, first of all, is this absolutely convergent? Okay, so this series, is this absolutely convergent? Okay, as usual, whenever you have the subtraction of a square root minus something that's not, what we can do is always transform it. So we multiply and divide by the converse, which is the square root of n squared minus 1 plus n, okay, plus n. And so in the numerator we now have the difference of the squares, so n squared minus 1 minus n squared. And then this is n squared minus 1 plus 1. Okay, so then we have minus 1 over the square root of n squared minus 1 plus n. Okay, but this now, sorry, so this is the absolute value of this, so the absolute value of this, the absolute value, and the absolute value of this, so this is a plus, okay? We can remove this absolute value, and we have a series of non-negative terms, okay? Now this is, we have this, the square root of n squared minus 1 is asymptotically equivalent to n, right? So this series, so this sequence is asymptotically equivalent to 1 over 2n, okay? So this sequence asymptotically equivalent to 1 over 2n, but we know that the series associated with this is divergent, so this series is divergent, okay? So this series is not going to be absolutely convergent, but is it going to be conditionally convergent? Okay, well, we have seen now that we can write this as n from n equals 1 to infinity of minus 1 to the n, and then minus 1 over the square root of n squared minus 1 plus 1. Okay, so what we can do here is we can write this as n plus 1 and a plus here, and then so we have this term that is monotonically decreasing, and it will go to 0. Okay, so according to Leibniz test, this series is convergent. Okay, so it is conditionally convergent, right? Okay, all of them are the same. Okay, let's go for 6. 6 is the sum from n equals 1 to infinity of minus 1 to the n times the logarithm of n divided by n plus 1. Now, the series of absolute, series of the absolute value of this general term is the logarithm of n over n plus 1. Now we can say that n over n plus 1 is n plus 1 minus 1 over n plus 1, right? So this is 1 minus 1 over n plus 1. Okay, so we know that the logarithm of 1 minus 1 over n plus 1 will be asymptotically equivalent to minus 1 over n plus 1. Okay, so as usual, but we have the absolute value of this, the absolute value of this, the absolute value of this, which is minus 1 over n plus 1. Okay, but now again, this is the variation on the harmonic series. Okay, but this is plus, but this is divergent, so the original series is divergent as well. Okay, now let's go to the original alternating series now. Okay, we have minus 1 to the n, and we know that this is asymptotically equivalent to minus 1 over n plus 1, right? So we can write this, and this, according to Leibniz test, is the limit of this is going to infinity, to 0, and so this series is convergent as before, right? Yeah, I just realized that I'm writing something, I'm abusing the notation. Okay, what we need to compute is the this series, okay, not the one that's this series and this series. Let me write this here. Okay, this series and this series, okay, are not the same, right? They're not the same. But the terms, when they're big and the n is big enough, the terms will be very similar. Okay, so what I'm saying is that yeah, I'm using the convergence of this, but I should be saying that, you know, this series, the logarithm of 1 minus 1 over n, is also a sequence that is monotonically decreasing and going to 0. Okay, so this is convergent, and because it is not absolutely convergent, it is conditionally convergent. Okay, so yes, sorry about this abusing of notation and confusing things. Okay, so please check that in the previous exercise these two series are not the same. Okay, but in order to compute the convergence, you can make this kind of arguments, right? And then we have 7, the sum from n equals 1 to infinity of minus 1 to the n, and then 1 minus the cosine of 1 over n. Okay, now we have the series of the absolute value of this, which is this. Okay, now 1 minus the cosine of 1 over n is, if you remember correctly, this is asymptotically equivalent to 1 over 2n squared, right? And so this, again, this is the series associated to this is the series of 1 over n squared, which is convergent. So this is convergent. So this series is absolutely convergent. Okay, and so now we don't need to check that the series of alternating terms converges, because automatically will be convergent as well. Okay, but if we use Leibniz test, we'll see that it agrees. Okay, okay, and so let's do the 8th part. Let's see. This is a sum from n equals 1 to infinity of minus 1 to the n, the logarithm of e to the n plus e to the minus n. Okay, so let me see how to work with this. We have the logarithm of e to the n plus e to the minus n, right? So we can say that this is the logarithm of e to the n times 1 plus e to the minus 2n, right? Is this true? So now, because of the properties of the logarithm, we can say this is the logarithm of e to the n plus the logarithm of 1 plus e to the minus 2n, right? And so this is equal to n plus, and then the logarithm of 1 plus e to the minus 2n. And when this is, so e to the minus 2n, when n is very big, it's going to be very small. So you could say this is asymptotically equivalent to n plus e to the minus 2n. Okay, but this is e to the minus 2n is negligible with respect to n when n is very large, right? So we can say this is asymptotically equivalent to n, right? So now when we have the series of the absolute value of this, okay, so this is 1 over the logarithm of e to the n plus e to the minus n. Okay, now this is asymptotically equivalent to 1 over n. Okay, so then it is divergent. But then for the original series, we can use Leibniz test, and so we have minus 1 over and then times 1 over this. But we know that this is asymptotically equivalent to n, so that means that this is a series that is monotonically decreasing and going to 0. Okay, so this series will be convergent according to Leibniz test, and because it is not absolutely convergent, it is conditionally convergent. Okay, and that ends the exercise.